right, thank you very much. Kind introduction. It's a great joy to be here. And so without further ado, let me just start. When I thought about this topic, I haven't talked about this at all, so I did what everyone does. I asked ChatGPT what I should talk about. And this is an abbreviated list of some of the things they told me to talk about. Talk about logistics and goods, that AI can actually help streamline the coordination of movement of people and goods, things like that. But Alex Lipton said he was going to talk about that, so I'm going to leave that alone. I will talk about energy management and optimization. I'm not going to talk about a few things, the logistics of disaster preparation and recovery and forestry and land use, but I will talk about how one could do these things to monitor carbon emissions and improve climate modeling. So an abbreviated list, I'm going to cover just 3 topics. Talk a little bit about weather extremes and how AI can probably manage distribution transmission systems required by renewable energies. It's no surprise that when you have renewable energies, you can't just turn them on. And it's a great interplay between when the sun is shining, wind is blowing, or standby power, battery power, things of that, and shuttling back and forth. It's been pointed out that AI is increasing in energy demand, and the question is, can we invent a new architecture? Already people are very motivated to decrease the energy of AI in 2 ways. One is in the software, making the learning more streamlined and making the queries have less scope. So they're editing the scope automatically. And finally, they're trying to do things in hardware. If you look at the NVIDIA website, they're bragging at how low in energy per unit operation the H100 is. It's about a kilowatt of power for 1 chip, but they claim it's very low compared to what it does for 1 chip. It also costs $30,000. The main servers, the Googles, the Metas, the people like that have hundreds of thousands, millions of these things. But really, can we invent something, an architecture closer to the brain? And finally, a little bit about climate modeling, the need for more economic models of carbon capture. Okay, so let's talk about weather extremes and the system. Let me remind you, a long time ago, that the electrical system in the United States in its present form, minus about 20 years, 10 years, really was very little different from the thing that Edison and Tesla, who worked with Westinghouse, managed. This is a picture of the Pearl Street station. And if you look at what we had in the early 1900s, you had telephone power lines like this and old cars. And the year 2000s, you just have more telephone lines on wooden poles. So there are some ongoing challenges. For example, there's congestion in the power lines. There's severe weather, natural disasters, and there's these market and regulatory complexities. But there are new challenges because renewables are intermittent, as pointed out before. There are also cybersecurity, physical sabotage issues, and the homes are having behind-the-meter sort of damaging systems. This is rubbing. I don't know how to stop it. Okay? All right? Okay. All right. So let's first start with the fact that there are major power outages that have been increasing. These are outages due to power, and they're increasing as we go over the last 21 years or so. And you've probably heard of the term atmospheric river. Let me explain to you what an atmospheric river is. It's a stream of water vapor in the atmosphere. It has a lot of water vapor. It moves very fast, contains a lot, and this is a satellite picture of such an atmospheric river. And let me play the movie. And you see it's beginning to rain, and it's attacking Northern California. This is a river, February 2017, where there was tremendous flooding in the California area where I lived in the Bay Area. I live next to a little creek that's maybe 5 feet wide. It turned into something quite a bit wider, and lots of furniture were floating down the river, as well as big trees. Fortunately, no bodies. But what happened in this is that there was so much rainfall that there was a dam in Northern California that was near breaking. This is the Oroville Dam. This is the dam on the left-hand side and the river reservoir. And this is the dam about a day after this downpour of water. In fact, you know about water. You've actually had a downpour maybe a year ago, and a famous picture of, I guess it was a BMW, goes under the water, chugs along, and then comes back up. And so BMW thought that was great. They're waterproof. Anyway, this dam, the spillway is on the right-hand side, and you see that the spillway is eroded away. This is an earthen dam. It's coming apart. And there was a real fear once that spillway starts to erode completely, the whole dam collapses. And 180,000 people downstream were evacuated. Okay, so this is some of the things that we now have to deal with. They seem to be coming more frequently, but the record's not clear because this is only in the last 5 or 10 years, and that doesn't really mean climate change quite yet. Climate change is 20 or 30 years of repeated behavior, but there are some suggestions that this is a wave of the future, that water will come down when there's higher temperature, there's more moisture in the atmosphere, and when there's more moisture in the atmosphere, more rain will occur, both on land and in ocean. Most of the rain is over the ocean, which is 70% of the surface area. But if the rain occurs on land in sudden downpours more than what we're used to, we have an issue. And the issue simply is when huge storms occur, we're just interested in flushing the water out of our streets, our homes, our cities, flushing them into the ocean, rivers and oceans. But if that's the water we're going to get, we actually have to capture that water. And the water systems around the world, I'll speak specifically about the United States, are not geared for that. They're geared to flush storm water and capture normal water. But if more water is storm water, we have to capture it all. And it takes decades to redesign the water catch system. All right, so how can AI stabilize the electricity transmission and distribution system? Well, let me reach back in history and show you a picture of a 2003 blackout in August in the United States. There was a faulty relay. The powers that be decided to blame the blackout on Canada. That's a joke in the United States. We always blame something goes wrong on Canada, like the last election. I'm just kidding. But it was there was a faulty relay, and then an operator error. The transmission line disconnected. Once the transmission line disconnects, it puts more load on the other lines, and then and that was on the threshold of breaking down. So as more and more disconnected, there's more and more load on the other lines, and it started a cascade effect that lasted approximately 2 days. And so the entire Northeast just went black. Remarkably, this is August 2023. 9 months later, there was a little baby boom. When there's nothing else to do, and you're dark at night. Anyway, so the reason I'm showing you this and remind you of this is that there are measuring devices. They're called phasers. And these phasers measure the voltage and the phase every 30 times a second. And you see in the hours 15:05 to 16:10, as these things were beginning to cascade, there was ample evidence that the system was failing. There was an hour. And so we had an automated system. This was not measured in real time. This was measured after the event and reconstructed. But if it could be measured in real time and you see this incipient failure, you can do something about it. Nowadays, we have a much more connected system, and so does Europe. And I was talking to the chief executive of E.ON. It's an international, based in German, electrical distribution company and transmission company. And they said when Russia bombs a power station in Ukraine, they see it in their electrical system. And then they have to give additional supplies of electricity to Ukraine because they see this bombing. And so there's a modern electrical system. Let me tell you a little bit about these phasers. The phasers are on the right-hand side. As I said before, they're measuring the voltage, the phase angle, the power transmission line, 10 to 30 times every 10 to 30 milliseconds, and they're generating petabytes of data. They relay this data via GPS to a central command system. When I was Secretary of Energy at the very beginning, I had what was called recovery money. It was about $34 billion of discretionary money. Never have I been so beautiful and witty and charming in my entire life. This is discretionary money, in addition to my $60 billion of normal budget money. And I spent some of it, a little bit of it, on these so-called power measurement units, or PMUs, 3,000. What was I thinking about? I wanted to distribute these all around the United States so these can coordinate the United States electrical grid system, which is comprised of three major areas. There's the Eastern interconnect in yellow, the Western interconnect in blue, and Texas has its own country. This doesn't mean there are only three power companies. There are hundreds. But these are the coordination areas. And the idea was that something like in a blackout occurs, you could actually catch it. And what I found after a year and a half of giving the utility companies these very expensive things, they're $5,000 a piece, they thought they were private property, confidential information, and they didn't share any of the information with each other, which means it defeats the entire purpose of knowing what's happening to the grid. So there was a come to Jesus moment. I called them back and I said, I gave you these for free. You got to connect them up, because it was for the robustness of the transmission and distribution system. They did do that, and there was a little burp a year later in Florida, and you can see the voltage and phase ripple go all the way to Florida, trickle up all the way to Canada, and go all the way back down, and then echo coming back down. You could see it. The fact that you can see it and you can measure it means, in principle, you can do something about it. Why can you do something about it? Well, in modern electrical systems, it's the old version of electrical systems, Ohm's law, Kirchhoff's law, is you start at a high voltage, you pour the power in, and just like water flowing downhill, it just trickles down everywhere, depending on the local resistances. But now we have reactive systems. We can induce capacitances and inductances to have active resistances that can actually put the power over here versus over there. And so for the first time in the last 10 years, we're able to divert the power, not by just pouring water at the top and letting it run down. We can put in little pumps and diverters and things like that at will, which is very, very good. But the coordination is very, very slow. Let me tell you about another problem, and it's the integration of renewable energy. California has about 70% renewable, carbon-free energy, I should say. 10% of that is nuclear. The rest is wind, solar, hydro, geo. And this is one day, and the yellow is solar power. And you see about noontime, there's so much solar power that they're producing an excess of energy. And so that energy is actually being thrown away. And in the last couple of years, California has installed maybe 30 gigawatts and gigawatt hours worth of batteries. That's very expensive batteries. They're a couple $100 a kilowatt hour. But because they're throwing it away, you have a very unusual thing. So prices become zero and negative during this time. And, and you see around 4, 5, 6 o'clock, the solar is turning off and there's a huge demand. And so this is, for those of you who don't know, any place that has a lot of renewable energy suffers from what we call a duck back problem because it looks like the back of a duck. And during the peak of solar times, there's so much solar energy power being generated that it becomes negative. And so in the past, we were throwing it away. And this is happening not only in the United States, it's beginning to happen in China and other places. So it's the management of this power via the control of the energy, and especially you need energy storage. Electricity demand so far is mostly inelastic. So this is a plot of a particular time of day it's an average of the summer from 2010 to 2012, and you see 2010, 11, and 12. And what it's showing is the cheapest energy gets dispatched the first. It's sent out. What's the cheapest energy? Well, it's renewable because they're fixed installment costs, and other than that, the fuel is free. So that's the first thing that goes. Nuclear power is the second cheapest because, again, CapEx has already been paid for and the nuclear power is there, and so the fuel is a small fraction. But as the demand grows, in the southeast of the United States, coal kicks in because in the southeast they still have coal plants and it's continuing. And then finally you see the yellow natural gas is kicking in because it's expensive relative to coal. And then finally, you end up burning oil. And as people in the Middle East know, burning oil for electricity generation is like burning $100 bills. And so the price is zooming up. And this price of $300 a megawatt hour can actually go over $1,000 a megawatt hour. Now, given that, and this only happens maybe 5 days out of a year, that you would want to have what's called real-time pricing. Real-time pricing means if it really begins to cost the utility companies, because they're bidding, most of the bidding is next day bidding, but there's 15-minute bidding going on, and as it looks like you're going to near power shortage, people are beginning to pay $200, $300, $400, $500 a megawatt hour to get electricity. If the customers knew that the system is being strained and it's costing the utility company this amount of money, and it would cost them this amount of money, they would say, oops, I don't want to run my clothes washer at this time, so let's not do this. Why don't the utility companies do this? Because most of the people aren't aware of what's really happening. So unless you have automated, smart appliances, again, a form of AI, a distributed AI, to actually say, we're in a power crisis, I'm not going to use anything, and you can sign up on a voluntary basis to shed your load, and the utility company can give you a lower rate. But the utility companies do not do this now because the less educated people won't know this, and they're the ones who pay the high rates. So we need automation to kick in before you can actually do something that's much more efficient. So that's an example. I should also note, in this time where you're sending a lot of electricity out of state during the peak noontime hours, you notice that the light blue is hydropower, and even though you're generating a surplus of energy, you're still letting the dams generate power. Now, in principle, you shouldn't be doing this. You should be saying, wait, I should be reversing the turbines and pumping the water uphill and getting what's called pump storage, which is the cheapest form of electricity storage we have in the world and will remain the cheapest form. So during this hot day where we're putting a lot of the energy into very expensive batteries, we're not turning off the dams because of environmental concerns. And so we have to figure out a way to allow the dams to stop the flow for 1 or 2 hours during the middle of the day to pump them uphill. Because then you'll have an enormous battery capacity. So you just want to make sure the fish in the river doesn't die in that 1 hour, which I think we can engineer. That's just a detail. Okay, so energy consumption of AI, it was mentioned before. And so here's a little one view of a paper written in 2015 of the energy forecasts for energy used in wireless communications, consumer devices, and the greenest data centers. Artificial intelligence is placing new demands on energy, and at the time of this article, a little bit after, AI really began to take off and blockchain technology was taking off. Roughly speaking, half the electricity of data centers is used to mine Bitcoin type currency. What is Bitcoin currency used for? Money laundering and evading taxes. So half the energy of electricity doing that is not a good thing. Personally, it should be outlawed. But in any case, since it's making people a lot of money, there's other forces saying, no, I don't want to outlaw this. But that's where we're heading. This is before AI really took off, so the projection was by 2030, maybe 21% of electricity demand would be in communications and computation. If you look specifically at computation, where the gray is energy consumptive enterprise data systems, the dark blue are these hyperscaler centers that Google, Meta, Amazon, and others use, and it is growing very rapidly. Part of the growth, of the rapid growth, is the fact that in these training models, like ChatGPT, you have lots of parameters, and in this plot, it's a log plot on the vertical axis. You see that the number of parameters, this is 100 billion parameters. And it's these very, very large models with these large parameters that are gobbling up all the time. So ChatGPT, for example, has 1.8 trillion parameters, 10 times larger than ChatGPT-3. So there has got to be something better than this. So let me give you something better than this. If you have a 4-year-old and a parent speaks one parent speaks one language, another parent speaks another language, and if they're well-to-do, there may be a third language in the house. And by 4 years old, the child is fluent in all 3 languages, can easily translate, knowing which parent or nanny they're talking to, and they can tell the difference between cats and dogs with very little training. Okay, so a little toddler uses about 70 watts, and half of that power goes into the brain. As you get older, a smaller fraction goes into the brain unless you have an intellectual life. Then you can be maintained while you're thinking, half the power going to the brain. Chess players, by the way, I had a postdoc who was a junior chess champion in Germany, and when he's playing a match, he said that you're eating food like double the calorie intake. It's actually like a marathon running in terms of the amount of calories you're consuming when you're in a 3-hour, 4-hour chess game. Anyway, so, and then the upper right, there's another young brain doing experiments in gravity. And so they can figure all this stuff out with very, very little programming, much less data. If you asked ChatGPT a year ago, when did the first elephant swim the English Channel? They said in utter confidence, the first elephant to swim across the English Channel did so in 1959. An Indian elephant named Jumbo made the journey for a publicity stunt organized by circus owner Bertram Mills. You ask now, it said it was actually a publicity stunt. Jumbo was on a boat and they towed him across the English Channel. So they fixed part of the error. But, total confidence. No fact checking. Okay, so let's wonder, can we do something different? And and is this 35 minutes my time, really? No. Okay, great. Okay, so let's figure out a different way of doing things. You can try to emulate a brain by having inputs, a lot of hidden nodes, and you have deeply connected hidden nodes, and you go back and forth in these digital neural nets, and then by adjusting the weights, you finally get an output. And so that takes a long time, this digital computation. And is there something else? Can we invent something else? And I'm going to briefly describe something that's been happening over the last 5 or 10 years. It's led by Andrea Liu, a theoretical physicist at the University of Pennsylvania, and her experiment, she's a theorist, and her experimental husband, Doug Durian. And they're saying, if you look at these artificial neural nets that live on a processor, you have a bunch of inputs, you have the hidden layers, you have the back propagation of these hidden layers, and finally, after many, many cycles, you can get an output. An output could be whether it's a dog or a cat. And then you compare that to a brain, and it doesn't need this processor. The learning is distributed, it's robust to damage, and it uses, this is different units, but it's still on the scale of 20, 30 watts. It turns out 2,000 kilojoules a day. This is taken from an Andrea Liu talk. It's about 20 watts. And the brain also controls other things while it's thinking. So what Andrea did is it said, let's take something really simple. And you consider a bunch of nodes connected by these lines, and each line is a resistor. And when you say apply a source, you're going to set a voltage on these sources, and you're going to say, okay, these resistances can self-program themselves, and what she wants to do is let this system adjust its own resistors to go to the lowest energy state, and you compare this clamped state where you have on the right-hand side the applied source, and let's see if it's not going to work. So you have on the right-hand side, you have the applied source and the desired target response on the right-hand side, and then you have the free centers. So if the applied desired target response is the clamped one, and you let the free one just adjust itself, what you want is a local rule of these resistors. Each node is connected by a resistor. The resistors are nonlinear. So you're trying to emulate the idea of a neural net and a feedback. And it's very important that the feedback be nonlinear. If it's linear, you don't get anything that you really want. And so these resistors are nonlinear. And Andrea said, let the resistors adjust themselves to adjust to the lowest energy state. And to model this, to abstract this, they said, we're going to have an applied desired result of certain currents in these blue things, and you leave the other ones free, and you let them both run. And so there's a local rule that is adjusting all the resistors, and it's doing it in real time. So when you make adjustments to the resistors, you're only caring about, each resistor only cares about its local environment to satisfy Kirchhoff's laws. You know, the current coming into each node, the current going out of each node have to be conserved, right? There's no, the sum of the currents has to be zero, and it just moves along. In the actual embodiment, it's of much fewer nodes, and these are what the resistors look like. And so, for example, in the output, you put in a voltage V1 on the upper left-hand side, and you have an output 0. The resistors are some transistor system that makes it nonlinear, and off you go. So in comparing the clamped one, where, for example, in this schematic, you have a voltage coming in, V1 in the upper left-hand side, and the output is 0. And in the free one, you're just sort of say, I'm going to see what the output is. The clamped one is what you want, but you're now going to adjust the system to get as close to what you want as possible. It's like when you do machine learning, you kind of have a vague idea what you want, cat or dog, but you have to figure out, well, it's not actually like that because they figured out cats and dogs without much human help. But in this case, the free one, you want the clamped and the free one, the difference between that to go to 0 by doing the resistors. So the whole trick of this is all the computation is done in real time, locally, in each node, and they only care about its local environment. But you can, if you have hundreds or thousands or millions of nodes, you do this all at the same time. Okay, so the computational speed up is when you have hundreds of thousands of nodes. And so when you let this thing go, I'm just going to skip to it. This is what it looks like. By the way, this is what each resistor looks like. It's a bit of a kludge. It's a digital resistor that has about 128 states, and it looks like this. And so when you let this thing run, and when you have a small number, and this is like 16 nodes, you have the input voltage and the output voltage, and you see that on the right-hand side of B, you see the output voltage after several iterations, 100 to 150 iterations of this automatic iterations. You're not clocking it; it's just doing its own thing. The free answer is approaching the clamped output, and then you can look at the resistances and say, aha, I know what the answer is. That's very good. If you take a very limited set of nodes and you snip one out, and you see in the right-hand side in A, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, something like 10 or so nodes. You cut one of them. Let's say you cut a purple one. Then the mean squared error goes down. It's collapsed onto the right solution. You cut out a node, the error goes back up suddenly because it's not the right solution anymore. But with one resistor missing, it finds it again. You cut out another one, it goes up, finds it again, and so on and so forth. And you can cut out one, 2, 3, 4, 5 of these, and it still finds the solution. So it is beginning to reproduce this robustness that we all know. When people have epilepsy, severe epilepsy, sometimes the treatment is they take away half your brain. And yet you can still talk and live a quasi-normal life. That's pretty good. You can't do this with a computer. And so this is also beginning to replicate this robustness of this. Now, this is just a toy experiment, but it is integrated electronics. So if you have 10 to the 7 edges over, 10 square millimeters, you get a lot of parameters. Now, it's not a given, and so what Andrea Liu and her husband Doug Durian are doing is they've made they've made each of those resistor things a little much more compact card, but they also have the designs in place now, and it's being manufactured. The high-performance integrated network, I think it's like 100,000 nodes or something like that. And so perhaps in a year or so, we can get to see what it really does, because the feeling is that this really scales very rapidly as you go from 10 to 15 to 100,000. And so it's not bad. You look at the human brain, we have about 10 to 11 neurons. An Apple M2 Ultra CPU has 10 to 11 transistors. Within a couple orders of magnitude, the same number of connections. The clock speed of the Apple is much, much faster because the brain has a much better architecture, and the energy consumption of the brain is much less. And so this is giving you a glimmer of something you can actually build in hardware. So let me stress, the usual neural nets are all done digitally, very clumsily, and a very time-consuming process that takes the hundreds of megawatts of these data centers. And if you can get a good architecture, you're down by many, many orders of magnitude. It's not clear that this will get all the way there. There is a challenge. The brains are a typical neuron is talking to 1,000 other neurons, and to get each transistor to talk to 1,000 other transistors when you have a total of 100,000 transistors is a topological challenge. But it's on its way, and it is very promising. Okay, so let's talk about climate change, climate modeling, and other things. This is to remind you that the global mean temperature, one of the UN targets was to try to stay below 1.5 degrees centigrade in this century. And we see in June and July, we're over 1.5 degrees. And I don't think we're going to come back anytime soon. So that's now at 1.6 degrees. The Sad news is that there's a lot of heat inertia in the system, and I said the oceans were 70% of the surface area, but the average depth of the ocean is about 3.5 kilometers. Huge heat capacity. The bottoms of the ocean are about 2 degrees centigrade. Very slow mixing time between the surface temperature of the ocean, which determines with the land temperature the weather, and the bottom of the ocean, which is 2 degrees. So it's like we have giant ice cubes. You've increased the greenhouse gas effect, so heat coming in, roughly constant, average over 11-year solar cycle. Heat going out less. Where's it going? Well, 90% of the heat is going into the ocean. So we don't see most of the warming of the planet due to the greenhouse gas effect because we got all these ice cubes in our glass. And how long does it take? 100, maybe 150 years to reach a new equilibrium. So the damage we've already done is invisible. Like you've been smoking cigarettes for 30 years, you've started a chain reaction of mutations that will eventually give you heart disease or lung cancer, but you don't know it yet. So that's where we are now. We do know that this is very closely associated with the greenhouse gases, carbon dioxide. Methane's 84 times worse, but it only lasts for about 10 years before it gets oxidized into carbon dioxide. Nitrous oxide, N2O, is much worse. It's 300 times worse greenhouse gas, and it lasts about 100 years. There's a problem with methane and nitrous oxide in that a lot of this comes from agriculture. This is a fraction of these potent greenhouse gases that are from agriculture. Unless you, for example, get rid of fertilizer, you're not going to get rid of the N2O emissions. 3/4 of the N2O emissions are from fertilizer that's not taken up by the plant. So in these scenarios of what might happen from 1990 to 2100, we're about here. We're a little bit above the current policies, and in between that and the no policies, we've passed the 1.5 degrees. We're not going to get to the 2 degrees. And so if you had to bet, I would bet we may end up, if we're lucky, at 3 degrees centigrade, not 1.5 or 2 degrees centigrade. And I already said that. Now, you've probably all seen graphs similar to this. In fact, this was in the last IPCC report. You simulate, use a climate model to simulate natural occurrences without the known human greenhouse gas emission, and you get something in the blue line. And you then put in the known greenhouse gas emissions that humans put out, and you get another simulated curve, and you compare that to the observed curve, and this looks pretty spectacular. The computation power can get down to scale resolution of 1 kilometer. It looks pretty convincing. Okay, so let me tell you a little secret, and there's an interesting article. This is the first of a couple, Remy Horden, and he says that the art and science of climate modeling. And so fundamentally what he's saying, I'm actually going to read it for you, but fundamentally he's saying, even at a kilometer, which is a massive supercomputer running for weeks or months, you can't really resolve some of the very fine scale stuff. You can't say much about water and precipitation and other things. And oh, by the way, climate models are terrible with precipitation. But there's more. And so what they do is they have the large climate model based on Navier-Stokes equation, gravity, all these other things, but they can't get to the fine scale, and they have these submodels, and these submodels, they try to get the fine scale stuff that has to do with condensation of water and clouds and things like that. And in a preprint to the thing that finally got published in the Bulletin of American Meteorological Society, they took out a very interesting sentence that was in the preprint, and it said, tuning is an essential, tuning of the climate models, they're hand-tuned, is an essential aspect of climate modeling with its own scientific issues, which is probably not advertised enough outside the community of model developers. It's interesting, that sentence was missing in the published one, which I find very amusing. So the secret is, these models are still hand-tuned, and they're hand-tuned to match with reality. Okay, So that spectacular agreement is gotten there because there was, a real intelligence doing something. Now, what has happened is there's been an attempt to use AI to do better climate modeling. This is an example. They had the normal large climate models, and they did it for a scenario where greenhouse gas emissions is low, a scenario where greenhouse gas emissions is high, and the conventional models then project what's going to happen in 2100. They trained neural net models on this, and as you all know, neural net models are good at interpolating. And what they found is that the interpolated model, on the upper left-hand side is the physics-based model, and the upper right-hand side is the AI-based emulator, which is just interpolating between the two extremes of the climate models, which they regard as their ground truth. Okay, this is no surprise because machine learning does a pretty good job of interpolation. There's been somewhat of a breakthrough. I'm not going to go into this, but I put this reference for those who are really interested. And they're doing something a little bit better, mostly better because they have better programming. These are the folks at Google. They got a prize for this work, which 2 years ago they got the prize. The paper finally came out this year. So they have inputs. They have the noise. They have the forcings. Forcings are, let's say, the increase in greenhouse gas effects. And they put that into a normal dynamical model. That's a normal circulation model. And then having to decide learned physics. The learned physics is that fine stuff like the clouds, the water droplets, things like that, which you can't model even at a kilometer scale. And so that stuff, they say, oh, we can't do this on a kilometer scale, so we can do it on the side, and we try to integrate this. And they do the learned physics with the neural net, and out pops what's going on. And this model got a prize because it was able to do up to 15 days ahead of weather prediction that really replicated the real state-of-the-art things. So it was no longer just interpolating as was done in the earlier work. It was actually saying, yes, we can predict up to 15 days what the weather is going to be like. 15 days is not climate, which is 15 to 50 years to 100 years. But there's evidence that the historical temperature trends over 40-year periods was also being demonstrated. And so this could mean that AI can provide a hybrid solution. You still have the normal, geodynamic models of climate, but the fine scale stuff you can't produce because every time you go up by a factor of 2 in resolution, there's 3 dimensions and 1 time dimension, so you go up by 2 to the 4 in compute speed, and it's even a little bit worse than that. And so there could be a possibility that these things could get better. But again, I'm saying right now they are failing miserably in precipitation. And at the moment, my biggest concern is what is the precipitation going to be like in the coming decades or 100 years? All right, let's talk about greenhouse gas emissions in general. There's many countries have made pledges by 2050 to go to 0 greenhouse gas emissions. What does that mean? It means you have to eliminate all the emissions from steel, concrete, plastics, chemicals, textiles. You have to eliminate all the greenhouse gas emissions from the food supply, and we do not have a solution for eliminating fertilizer. We're 8 billion people going to 11 billion people. The developing world desperately needs fertilizer. We can't feed them. And so without fertilizer, we've got a problem. But with fertilizer, we've got another problem. We've got the N2O emissions. And most of the N2O actually comes out of the soil. What the plant grabs, a quarter of the fertilizer, is fine. That doesn't go into greenhouse gas emissions, but most of it doesn't. Most of it doesn't go into river runoff. If it went to river runoff, that's the algae blooms, we could get rid of it. But if it's coming out distributed in the soil, it's another problem. So anyway, with that, we're likely to go over 550 parts per million CO2, and we have to capture carbon dioxide from all these sources. And now the costs from a point source and 100 sources, these are kind of plausible costs if you have a hope of doing this, but it's not there yet. Point sources are over $100 a ton, and direct air capture maybe $300 a ton or more. We're emitting 52 gigatons per year, and so given all the hard to abate emissions, until we get sustainable aviation fuel made from ultimately made from photosynthesis, until we get a substitute for fertilizer, which could be microbial genes entering into symbiotic relationships with plants, just like soybeans use microbes to feed them. There is research being done, and we can do this with corn, and eliminate half the fertilizer, but it needs to be done with all the grains and all the fertilizer in all soils. And the development time of the first experiment took 10 years. So that's too long. So there is a hope. But until we get all these things, we're going to need to capture 10 or 20 gigatons of air. That's a lot of stuff. CO2 stored at high pressure in saline aquifers. It can be a supercritical fluid. It's got a density about 70% of water. And you look at, by comparison, all the landfill in the world today is about 2 billion tons. This density is about 5 times lower, but it's 10 times more. So it's 50 times more than 2 billion tons. So it's 100 billion tons, 50 times more than all the landfill of the world you've got to sequester every year. But never mind, let's see how we can do it. The current technology is you have chemicals like amine in these large towers. This is a amine capture tower in Petronova. When I was Secretary of Energy, I funded this. It was the first carbon capture project that was on budget, on time. The budget was $1 billion. It captured 1/4 of the carbon dioxide from a medium-large coal plant. And that little circle has an American-sized pickup truck. So this is a very big thing, and it's very costly. There are other attempts to put amine molecules on light porous materials like metal organic frameworks. This company, Svante, I've been on board of directors of this company for a decade. The idea is that this less heat capacity could perhaps be more efficient, but in the end, it's about the same. But and the problem is, when CO2 captures on amine, you form the covalent bond with the CO2. When you want to release it, you've got to heat it up. Okay, so let me talk about another way that we stumbled on in my lab, and that is, it's been well known that if you take water and make it very alkaline, so the pH is 12, 13, 14, you can store a lot of carbon in the water. And what happens is the CO2 gas goes into CO2 dissolved in water. It forms carbonic acid, H2CO3, but in very alkaline conditions, lots of extra OHs. That carbonic acid breaks up into hydrogen. It's not a sole proton, but it's surrounding a water, so we call it hydronium, but it's like a hydrogen ion with some surrounding water shell, and bicarbonate. That positive ion combines with surrounding OH because it's alkaline to make water and bicarbonate, but it's high pH, so the bicarbonate breaks up into carbonate, CO3, 2 minus, and 2 protons. And that's great. Large amount of carbon dioxide in water. And so what do you do? Oops, there's too much writing in this. Why did I make so much writing? Ignore the fine stuff. Let's talk about the basic physics. If you take CO2 at low concentration and make it a high concentration, you have to pay a minimum entropy price, because nature wants to take high concentration, you let it go, and it dilutes itself. So going from low to high concentration means that there's a minimum entropy price. The free energy entropy price is given by the gas constant times the temperature times the natural log of the ratio of the two concentrations. And going from 8% CO2 to 1 atmosphere of CO2, the amount of energy is only 6.26 kilojoules per mole of carbon dioxide. Direct air capture only requires 19.4. So what are these processes now taking? They're taking between 60 and 100, not 6. So 5 to 10 times more energy than is required by minimum thermodynamics. And so the question is, can you do better and get closer to this minimum thermodynamic limit? So the answer is, in high pH, we know that you can store about 0.4 moles of carbon in water. That's 0.4 moles per liter. 1 mole, just to remind you, of carbon dioxide at standard temperature and pressure is 22 liters. So 1 mole in water is 1 liter. So there's a 22 times concentration, okay? And so when you have electrochemical methods, suppose you increase the proton concentration from low to high. Let me go back and remind you of this chart on the right. You're capturing CO2 at very basic conditions, pH 12, and suppose you make the pH go down to 5 or 6, then your solubility of the carbon dioxide drops by 3 times 10 to the 4. Big deal. And so when you do this, it will eject the CO2. But in order to go from base to acid, you have to increase the proton concentration, you think. But it's the same thing. When you go from low proton concentration to high proton concentration, you pay the same entropy price. You can calculate what that is. And that's not negligible. It's about 35 kilojoules per mole. To add on to at 8%, it was about 6 kilojoules per mole. Still less than 100, but it's bad. So the question is it possible to change the pH without changing the proton concentration? You ask ChatGPT or Perplexity this and said, no, pH is the log of the proton concentration. They were wrong. pH is equal to minus the log of the proton concentration times a fudge factor called the activity factor. That fudge factor can be greater and less than 1. And so what we figured out by accident how to do is to change the fudge factor. And so let me describe the experiment in my remaining couple of minutes. We bubble in CO2, let's say 20% CO2 in this particular experiment, and then we turn on a current. We have a molecule in there. It's called tempo. It's being used, it's being considered for redox batteries. It's a very cheap material, very stable. And so in part A, that's the structure of the molecule, and it has a reduced state, which is neutral on the left-hand side, and it has a charged state where the charge is a positive charge, mostly residing on the nitrogen molecule, nitrogen atom on the right-hand side of part A. So we just turn on the current, and then we just pump. As you turn on the current, bubbles come out of solution. Because bubbles come out of solution, we do again this analysis of the bubbles, and it's about 93% carbon dioxide. There's a few percent water vapor. We don't know what the rest is. Okay? So that's what happens. And what we find, remarkably, is that we take this molecule and turn from it's in a neutral state, you oxidize it, you turn it into a charged state, and the pH drops precipitously. When you oxidize molecules from 0 to 100%, the black dots of the pH change from 9.5 down to roughly 2 and then some change. And it's following the log of the number of tempo molecules you've oxidized. Now, when you oxidize it, it takes a certain voltage to oxidize. And when you reduce it, it takes a certain voltage. And this cyclic voltammetry curve in part B, where you're going round and round and round, this is really remarkable because what we notice is that the potential, it doesn't change no matter what the pH is. So let me tell you in a cartoon form what's really happening. When you have this oxidized molecule, the nitrogen is partially charged with a positive charge. That positive charge then polarizes nearby water molecules. So in this cartoon, it's not a cartoon, it's molecular dynamics snapshot of the water. The oxygen is, and the two hydrogens are the white and red guys. And you see that water molecule is polarized. Now, suppose there's a chemical reaction, for example, that takes a proton, combines it with bicarbonate, and goes into H2CO3, neutral carbonate. Okay, so it's a chemical reaction that goes back and forth, but suppose it goes to the right. That carbonate could go and combine with another H to form CO2 and gas and leave the thing. But it's in an equilibrium condition, so it stays where it wants to stay. But suppose a proton is used up, what happens is this polarized water molecule, those protons on that water molecule are ever so slightly more likely to dissociate than a normal water molecule. And so when that proton gets used up, another one pops into being. So as a proton is used up, this is acting as a buffer of other protons. It doesn't make more protons. If you made more protons, you've changed the pH by changing the proton concentration, you pay the entropy price. But so think of these as standby reserve draftees. You're in a war, soldiers get wounded or die. You go back to your civilian population and say, I need more soldiers. You don't pay for more soldiers, you just draft them as needed. So this, we can do an experiment where you put this oxidized molecule in low pH, lots of protons, and you start buffering in OH minus, and this thing keeps the pH roughly the same until around 0.004 moles of KOH, and then all of a sudden the pH changes. Why? At that point, the number of OH minuses you put into solutions equal to the number of these molecules that are oxidized. So once this water molecule, a proton gets pulled off, that molecule is used up because that OH minus clings around that molecule. So after all the molecules get used up, then it no longer can buffer. But the solution of molecules is 1 mole, whereas I remind you, pH of 7 is 10 to the minus 7 moles of protons and 10 to the minus 7 moles of OH. So when you put in something 1 mole, you can drastically change the distribution of protons and things and OHs. And so the idea is you bubble in CO2 on the right-hand side. It saturates. There's some interesting energy kinetics there, but then you oxidize the molecule. It turns acidic. When it turns acidic, it has to follow the equilibrium laws, and out pops the CO2. And so in the upper chamber, the CO2 is released. You whisk it away. So you go from, let's say, a solution, a saturated solution at 10 or 20%, and finally it comes out as pure CO2 and a little water vapor. It takes energy to take the electron off this molecule on the right-hand side when it goes from a reduced oxidized state. But as the molecule returns, it grabs back all that energy, and it grabs the electron. And one can show analytically that if the pH dependence of the oxidation reduction doesn't change with changing pH, the return round trip of the energy you need to take off the electron, the energy you get back when you grab the electron to turn to reduced state is 0. Okay, so the only energy is the energy used to move the fluid and the resistive energy in this electrochemical cell. And so instead of 0.55 volts, we observe 0.22 volts, 50 times less, but 40 times less. But that resistance, that loss is actually due to resistance in the system that we know we can go down by at least a factor of 4 or 5 by using better membranes and better engineering design. So we think we're an order of magnitude below what is needed to shift the pH. It does all the right things. Bicarbonate comes out. I don't want to go into that, but in my remaining time, let me just summarize and say that this is much smaller than these large amine towers. The energy penalty, which is a major cost, is reduced by a factor of 5 or 10. The material is much more stable than amine compounds by a long shot and much cheaper. And the capital equipment is maybe 1/2, 1/3, 1/4 the size. Now, there is a better form of carbon capture, and that is used plants. And the crops we eat capture between 9.5 and 18 gigatons per year, but most of it gets recycled. That's why reforestation is important, but eventually the forests saturate. So I'm going to propose a new building material that can perhaps replace the high carbon building materials we use today in steel and concrete. The new material is called wood. Wood structures from cultivated forests, not from virgin forests. can be made into laminate girders that can replace steel and concrete. This is a building in Norway, 20 stories high, where there is no steel and concrete, it's just wood. And we know how to keep wood going for a long time. Old London has 1,000-year-old buildings. The Forbidden City in Beijing is 600 years old. So wood lasts a long time. The only trouble is we tear down buildings in 50 years, which there should be a law against also. You should build a building and make the shell last hundreds of years, and you modernize the HVAC systems and communication. Leave the shell alone, because not much of the building except the steel and the copper are recyclable. And so I think government policy can do this. And if you keep buildings for a couple hundred years, you sequester carbon for a couple hundred years. And you grow more timber for the laminated wood. Okay. Now, you've been told we're in a transition. This is in the United States, where we went from wood to coal, beginning in 1850, and then by the early 1900s, we began to discover, late 1800s, began to discover oil and natural gas, and you see that we're replacing coal with petroleum and natural gas, and then we have nuclear and other renewables at the tail end, and so perhaps we're on this transition going to a cleaner energy source. That's nice, but that's the United States. What about the global energy transition? And the sad answer is, whenever we find a new form of energy, we just add it. We don't give it up. And so here we have coal, oil, nuclear, natural gas, and it's just rising. And so this is going to continue, especially in the developing world, because coal is so cheap. And how we can get around this will require a lot of transfers of money and really ultimately better technology. So in closing, we're still on a collision path to about 3 degrees. Think of us on this giant ship, and there's 2 sailors in the crow's nest, and they're looking ahead and they're saying, "What is that thing ahead? What is that thing?" "That's an iceberg." Say, "Cling, cling, cling," and they say, "Iceberg ahead, iceberg ahead." And then in the movie Titanic, you see all this dramatic clanging and people running and reversing the engines. They didn't reverse the engines, by the way. They just did hard rudder. But it made better dramatic cinematography and lots of exciting music. And the poor kids on the crow's nest are saying, "Turn, why aren't we bloody turning?" And the answer is, it takes 60 years. Thank you.